Thank you, Emanuele. All right. We can start. Questions? Comments? So today we collect what we learned so far about heat flow and differential calculus integration by parts of metric measure spaces, and start really working on this class of RCD infinity spaces. Then I'm going to define later on. For the moment, let me recollect this setting. So questions? So let's start with the CDK infinity space. For simplicity, in my proofs, I will always, and perhaps also in my statements, so that I don't cheat, I will assume sometimes compactness just for simplicity, although that is not necessary. All right. So recall that we have defined well, at least one heat flow. So one version. So first version. Well, I mean, we have two equivalent definitions of heat flow. So heat flow can be seen as so the gradient flow of the achieved energy in the space with respect to the distance L2, and the gradient flow of the relative entropy with respect to the geometry of the distance W2. Okay. Now that's also in general CDK infinity spaces, and we are seeing that in fact this viewpoint makes it evident that this heat flow is in general nonlinear. Okay. And I've already made a comment that on Riemannian manifolds heat flow is linear. It seems like a reasonable idea to see what happens, what we can learn about these spaces if we make the further assumption that the heat flow is linear. And perhaps I should also add that the heat flow is stable with respect to measure Gromov-Hausdorff convergence. Right. So the linearity of the heat flow, or in some sense, whatever condition you put on the heat flow, passes to the limit and provides a stable notion. So it makes sense to study these spaces where the heat flow, CDK infinity, where the heat flow is also linear. So because this is still a stable class of spaces. Now, and if you remember a couple of lectures ago, I said, okay, well, as nice as or natural as this idea can be seen, the point is not only throwing definitions, but actually proving statements about the definition that are thrown on the table. So what can we say about a CDK infinity space or a heat flow rate or whatever else if we further assume that the heat flow is linear? Okay. And today we start seeing this. And let me start discussing two crucial formulas. So two propositions, both are basically from my papers with Ambrosio and Savare in, I guess, 2001. So X CDK infinity, let's say compact, it's not needed, but and let pick probability density, which is also in L2, so probability density, so it's not negative. So we know in particular from the mass preservation and the weak maximum principle for the heat flow, we know that if we consider the gradient flow trajectory, okay, the heat flow, say in L2 starting from F, then we know that Ft is always a probability density, sorry, for any positive time. Okay, and we also know that the curve that takes t and returns mu t, which is Ftm, this is locally absolutely continuous with respect to the distance W2. Right? Because it's also a gradient flow of the relative entropy. So in particular, this is true. Okay. Now, the first formula that I want to study is is the following. So in particular, if this curve is absolutely continuous in a metric sense, for every measure nu, probability measure on x, the curve, the map that takes t and returns, say, 1/2, the squared Wasserstein distance between mu t and nu is, this is absolutely continuous, locally absolutely continuous. This say on the interval, let's say it's 0 plus infinity. Right? An absolutely continuous curve. I'm post-composing with a distance function squared. Okay. So it is absolutely continuous. It is differentiable almost everywhere. Okay. And I can tell you who is this derivative. This derivative, and that's the formula. Then dt of 1/2 W2 squared mu t nu. This is equal to, let me write it this way. Actually, no, let me write it this way. So this is equal to the integral of phi t Laplacian of ft dm for almost every t, where phi t is a Kantorovich potential from mu t to nu. So I'm getting a formula here. All right. Let me first of all read this formula, and then we'll prove this. First of all, I'm telling that a certain derivative, I'm giving a formula for almost every t. The existence of this derivative I've already commented. So by absolute continuity. Now let's look at the right hand side. And let's notice that given that I assumed the space to be compact, any Kantorovich potential, in particular, is a distance squared over 2 function, must be Lipschitz. Okay, global Lipschitz and also globally bounded. Okay, so the Laplacian of ft is an L2 function. This is bounded, so in particular it's also in L2. M is finite, say probability. So the fact that this is, well, it's an integral function poses no problem. And I did not quantify, I did not make any quantification on phi t, and this formula is true for any phi t. No? There is no statement about uniqueness of Kantorovich potentials in general. Okay, but whatever you pick, the formula holds. Okay, so the function can change, but not the value of the integral. Proof, and the proof is trivial. I mean, if only all the proofs were like this. Okay, pick a point t where the derivative exists. Almost every does the job, and pick any Kantorovich potential phi t. Okay. Then we know by definition of Kantorovich potential, we know that we get equality in the dual problem, right? So we know that 1/2 W2 squared mu t nu is equal to the integral of phi t d mu t plus the integral of phi c. Right? On the other hand, the couple, sorry, phi t c. The couple phi t c is an admissible couple in the dual formulation of the optimal transport problem. So for any other time, say for instance t plus h, we have that this is greater or equal than this. Right? So let's make the difference. This simplifies. And this is mu t plus h. Remember that mu t is ftm. And this is ft plus hm. Right? And then use the fact that dt of ft is equal to the Laplacian of ft to go. Right? Make sense? Right? If you want, add, I did tell that the right derivative of ft is equal to the Laplacian of ft for every t, but if you don't want to use that result, you say, let's say that this equation is also satisfied for almost every t. So pick a t where this derivative exists and this is equal to the Laplacian, and where this function is differentiable. Pick the t and then you're done. Okay? All right. I made no use of the linearity of the heat flow in this proof. Okay. Second key formula. And again, I mean, this comes from my work with Ambrosio and Savare. And okay, perhaps I should also mention a paper with Ambrosio, myself, Mondino, and Rayala, where these things have been, worked out in the non-compact case, where a bit more complicated, but I will stick to the compact case. So again, x cdk infinity. And now I will compute a totally different kind of derivative. I pick, let's say that, say S to nu S is a W2 geodesic of bounded compression. So, so nu S is less or equal than some constant time reference measure M for every S in 0, 1. And let me also assume that nu 0 is bounded from below by some other constant, little c. Okay. And let me also assume, so now this guy is say, well, let's write nu s, let's write in eta s m. And let me also assume that eta 0, so the density of nu 0, is Sobolev. Right? It's a regularity. I'm adding a lot of regularity assumptions on this. And let's compute. Well, and well then, let me compute the limit as s goes to 0 of the, let me take the sort of right derivative at 0 of the relative entropy. If this derivative exists, that's the right derivative. I'm just taking the limit as of now. Well, this is greater or equal than the integral. I don't remember. There should be a minus, I guess. Yeah, let me write it this way. Minus d minus eta zeta grad phi d. Where phi is a Kantorovich potential. From for the geodesic, so if you want from nu 0 to nu 1. Right? You remember this quantity, d minus f nabla g is something that is always well defined for any couple of Sobolev functions. So as before, phi, given that phi is a Kantorovich potential, it is Lipschitz because my space is compact. So Lipschitz in particular is Sobolev, right? So this expression is well defined. Eta 0 is Sobolev by assumption. So okay. All right. And this I mean this formula is really crucial. I cannot underline enough how important it is. And yeah. Okay. Well, you would see in the applications why this is important. So let's prove this. Let me compute this guy. Let me notice that the entropy of nu s minus the entropy of nu 0 divided by s. Well, this is equal, by sort of by definition. This is let me write u eta s minus u eta 0 divided by s, where u of z is z log z, right? By definition. Right? Now, u is a complex function. So at any point, I have the inequality. So this is an inequality, if you want, that holds even without integrals. Right? Because, no, I'm just using the u at b minus u at a is greater or equal than u prime at a times b minus a. That's, you know, a direct consequence of convexity. Okay. All right. Well, then now I pick. So I lift the geodesic in W2, and you know, and I get a test plan pi. Pi is a lifting of nu s. Okay, so it leaves is a probability measure on the space of curves with nu s as marginals and with energy which is the same as the energy. Okay. Now, and notice that given that I am lifting a geodesic with bounded compression, by Ayala's theorem, or Ayala's lemma that we made last time, pi represents, well, pi represents, you know, the gradient of minus phi, right? In the sense that we discussed the other time. And on the other hand, what do I get in here? So let me you know, let me continue here. Yeah, this is the integral of u prime eta 0. Let me write it this way: in gamma s minus u prime eta 0 gamma 0 d pi of gamma. This quantity is the same as this. I just used the, you know, the fact that the marginals of pi are the etas. Make sense? Right? What's the integral of this function at gamma s is equal to the integral of the same function d es push over pi. But es push over pi is nu s, right? Make sense? Oh, divided by s. Divided by s. Okay. So when we take the lim-inf over here, lim-inf, this is, you know, if you want, is greater or equal than the lim-inf as s goes to 0 of this expression. Right? But now we can use the formula for, you know, the first order differentiation formula, the horizontal and vertical derivatives that we done the other time, and this is greater or equal than the integral of d minus of u prime eta naught applied to, you know, nabla, if you want, minus phi, let me write this way. And then this should be evaluated in gamma naught d pi, but so this is eta 0 dm. All right. Okay, but now we are done, right? So this, I mean, I have one homogeneity in this guy. Or perhaps let me keep it this way. Let me keep it this way. Let me write this way. Positive homogeneity if I don't make any further assumption. And I have the chain rule over here. So u is z log z. U prime is log z plus 1. And when we differentiate one other time, this is, you know, u second. You know, this is like by the chain rule, right? This is u second eta 0, and then I have d minus, you know, eta 0 grad, I mean the correct thing, eta 0, but u second is 1, huh? U second is 1 over z, so this simplifies. Okay. All right. Okay, so we have these two formulas that are valid on an arbitrary CD. Okay, perhaps I should say on an arbitrary CDK infinity space. In fact, it's not that I ever used really the CDK infinity condition, to be honest. I didn't really use CDK infinity. I mean, as far as the assumptions are true, you know, about the regularity of F naught or regularity of u0, these formulas are valid. Okay. Now look how close these two things are. This guy and this guy. If only calculus in our space was Hilbert's-like. You see this expression. So this is, if I integrate by parts, this is basically up to a sign. This is the differential of phi applied to the gradient of it. Here is swapped, so up to a sign. Okay, there is the differential of phi applied to the the differential of the density of the measure applied to the gradient of phi. Okay, and I guess let me write it here. So if we combine this, we get the following result. Here. And this is the starting point, if you want, of the theory of RCD spaces. So and now I really need CD to infinity. Okay, this I don't need. I put for simplicity. With linear rate flow, with infinitesimal Hilbertian, right? Infinitesimal Hilbertian. Then, and also let's say mu0 and mu be probability measures. Let me say with bounded densities, so they both have density bounded from above. And let me also say that mu0 is also density bounded from below. Okay. Then for almost everything, we have the derivative of the square distance between mu t and nu plus the entropy of mu t plus k over 2 the distance squared between mu t and nu is less or equal than the entropy. Okay. This is an inequality. It's a pretty important one. I mean, the rest of, I first proved this inequality, and then for the rest of today's lecture, I basically study this differential inequality. That encodes a lot of informations. So let's prove it. So I'm just stating there are certain inequalities. Okay. So let's. The proof now, with all the tools that we've done, that we've built so far, the proof is, very easy. Why is that? Well, first of all, I can compute this derivative at almost everything. So we can use that formula, and notice and recall. Perhaps first of all, notice the following: that for every t positive, if I call, okay, I didn't say who is mu t. Mu t is the heat flow starting from mu0. That, of course, you can interpret either as gradient flow of the Chigre energy starting from the density of mu0, or as the gradient flow of the relative entropy. Okay. Now what I wanted to say is that for every t bigger than 0, of course, mu t has a density, and this density, by the weak maximum principle, this density is bounded from below by a constant and from the above by another constant, right? Because these bounds are preserved by the weak maximum principle, and moreover, P is also Sobolev. Right? Why is Sobolev? Well, because if I do the gradient flow of the Chigre energy, doesn't matter where I start, for every positive time, I end up in the domain of the Chigre energy, which is the Sobolev space. Okay. And moreover, for every t, I can use Rayala's lemma. There exists a geodesic, and let me call it new, say, st. So t here is a parameter, is a index is the new, and S is the index for the geodesic, W2 geodesic from mu T to nu, okay, with bounded compression. And such that the convexity inequality is true, so the entropy of nu st is less or equal than 1 minus s the entropy of mu t plus s the entropy of nu, and then there is the correction factor, what is minus T1 minus T, the square distance. Right? So Rayala tells that I can select a geodesic. I mean, if I have two measures with bounded densities, and I'm sitting on a CD K infinity space, say compact, well, then I can find a Wasserstein geodesic connecting them, such that not only the convexity inequality is true, okay, that's lost through Villani by definition of CD K infinity, but I can select this geodesic, I mean, so smartly that it has bounded compression. Okay. Well, then what do? Well, then I collect what I know, and I'm done. So I also, pick phi t Kantorovich potential. Kantorovich potential from mu t to nu. Well, then this formula holds, and well, this is equal to to this formula that now I am in infinitesimal Hilbertian space. So now I can write this grad phi t grad f t. Yeah, right. By infinitesimal Hilbertian, this quantity is something that we have defined at the other time, and now this is within. And on the other hand, the element as s goes to 0 of this entropy, what it is, a nu st minus the entropy at nu t. Nu t is basically nu 0 t divided by s. This is greater or equal than what is the formula here is telling me. In this infinitesimal Hilbertian case, where I can, the expression is bilinear and symmetric. This is equal minus f grad ft grad phi t dm. See, now these two are the same. Right? Okay. In general, they are not, but infinitesimal Hilbertian tells me that these two things are the same. Okay, but I am done because this limit is also less or equal than, I mean, just by the convexity inequality, it is less or equal to the entropy, at the value s equal 1 minus the entropy at value s equals 0 and minus the correction term. K over 2 would distance squared. I mean, it's a direct consequence of the convexity inequality. If you want, what I'm telling, if k is equal to 0, what I'm telling is that if I have a convex function and I compute the right derivative at any point, this is bounded from above by the difference quotient at later time. Okay, end of the book. Right? Because this derivative is less or equal than this limit, but this limit is less or equal than this difference. It's really, there's no cheating. Huh? Okay. Now that inequality, questions? Now that inequality that I wrote over there is, so that has not been okay. It's not been adapted to the current time zone. Okay. What was I saying? Yes, that inequality, that differential inequality is so important that this deserves a name. And let's study a little bit the properties of. Definition. If you want now, I hope I forget everything about CDK infinity spaces and metric measure spaces, and I go back to discuss the notion of gradient flow in a metric setting. So let XD be a metric space, and E a function from X. For simplicity, I put in non-negative and lower semi-continuous. Lower semi-continuous should be there. Non-negativity is just, you know, for me because I'm lazy. And then I say that the curve is an AVI, you know, an AVI K gradient flow trajectory. If so, this is a curve that finds A naught plus, so it should be continuous. Continuous on 0 plus infinity. Absolutely continuous on the open half-line, or locally, absolutely. 0 plus infinity. And for every y in X, we have the dt. I mean, that inequality over there should be true. Okay. EVI stands for evolution, variation, inequality. Okay, is a variation inequality. Okay, concerns evolution. Okay. Decay is this. Okay. Now, why gradient flow? I mean, this doesn't look a priori gradient flow at all. Okay. I'll comment on the about this in a second. So this definition has been introduced by Ambrosio Savary and myself in our book on gradient flows, and has been extensively studied, especially by Savary and collaborators. And I will recall some of the results that they got in a moment. First of all, well, perhaps, and first of all, informally, what has this to do with gradient flows? And as usually, it's a good idea to start from the smooth case, you know, RD with smooth functions. Smooth and convex function. You know, example. I mean, motivational example. So let E from RD to R be smooth and convex. And remember that if E is convex, then grad E at X is the only, you know, is the only vector V for which, you know, in RD if you want, for which I should say in tangent at X RD, which is RD, such that the energy at X plus V scalar product Y minus X is less or equal than the energy at Y for every Y in RD. Well, now notice that, so I can further observe that this quantity, if I am on RD and RD, you know, on a Hilbertian space, this quantity is also equal to the derivative Oh, sorry, no, this is wait a second. So in some sense, so xt is a gradient flow. Okay, if and only if I have that the energy of xt plus actually yeah, plus this way. So xt prime xt minus y is less or equal than the energy of y for every y and t. I just replace v. If you fix a t where x, say, say the x is a smooth curve, everything is smooth, fix t, then xt prime is minus the gradient of v, if and only if for every y these holds, and I swapped x and y here to take into account them. This an equivalent character for if E is convex, of course. Well, now an observation is that okay, but this guy is the derivative of 1/2 xt minus y squared. Right? And now so you see I characterized being a gradient flow via means that have a metric analog, saying that xt is a gradient flow if and only if the energy of xt plus this derivative is less or equal than the energy of y for every y and t. Okay, this is makes sense in the metric space, and that's the definition above. I mean, for these convex, I mean, if you put k convex, you get this correction term over here because you have a correction term in k over here, but that's not conceptually there's nothing conceptual about that. Okay, very well. So these, if you do, perhaps a warning, if you try, or, I mean, an interesting warning, if you try to do this on RD where the distance comes from a norm, this equation, this inequality does not characterize gradient flow. Okay? Here we use in an essential way the fact that the distance comes from a norm, so that we can differentiate things, this way. Okay, try if you wish, and see that something goes wrong. You have in some sense goes wrong the same thing that goes wrong. We had to use the Hilbertianity in that computation of the derivative of the energy and the computation of the derivative of the distance in order to get a certain bilinearity, which is exactly what goes wrong if things are Fissler. Okay. All right. So motivated by this, we say that a curve is an AVIK gradient flow trajectory provided this inequality exists. Okay. Now there is at least one thing which is a little bit unpleasant here, and namely is the fact that basically you have to decide in advance the value of k. So you question yourself whether the curve is an AVIK gradient flow, and and the k appears in the definition, whereas for gradient flows in the energy dissipation sense there is no k, right? And well, that's it. Okay. I mean, we can work out. In fact, strictly speaking, I could remove this k, but I will not. Okay. So that's it. And in some sense, the reason for this, and this, if you want, is a bit evident or more evident from this example, is the following. This inequality encodes the fact that, or if you want, this inequality, the fact that for every x, pick a smooth function E on Rd, and wonder whether for any x there exists V such that this is true for every y. If this happens to be true, then your function is convex. Okay? Because what I'm telling is that for every x you can find an hyperplane that is touching from below the graph of the function. And if you think about this a little bit, you see that this implies the convexity of the function. Okay. So in some sense, this inequality is encoding, in some sense, is encoding the convexity of it. Okay. And also because of this fact that we are differentiating distance squared and imposing the certain nice properties, it is also encoding the fact that some Hilbertian condition on small scales, in some sense. Okay. So in some sense, we do expect that this inequality, also in a metric setting, encodes some k convexity property of the energy and some Hilbertianity at small level, and we will see later on in which sense. Okay. All right. let me perhaps add a couple of basic considerations about these EVIs. Then we take a small break. So, remark or proposition. The following are equivalent. So xt is, an AVI K gradient flow trajectory. For the functional E. Two. The inequalities of distance squared x s y minus distance squared x t y divided by 2 plus the integral from t to s of the energy of xr plus k over 2 distance squared xr y dr. This is less or equal than s minus the energy of y, and this should be true for every y and for every non-negative t and s. Okay, so what I'm saying here, what I'm gaining here by integrating in time is the fact that now this inequality is true for every t and s. Okay, 3, same as the original one. This is star, but with lim sup as h goes to 0 of distance squared xt plus h y minus distance squared xt y divided by 2h in place of dt distance squared. And 4, same as above, but only for y belonging to a certain d dense. Okay. All right. Let me prove this. So the fact that 1 implies 2 comes just by integrating this. I've just integrated this inequality, that is an inequality concerning the derivative of an absolutely continuous function. I'm integrating from t to s. Okay. I can extend this up to t equals 0, even t equals 0, just by first writing it for t positive and then letting t go to 0, and the left-hand side is continuous in t. Okay. So that's okay. Now 2 implies 3, because just write 2 with s, which is equal to t plus h, divided by h, and let h go to 0, and you get what you want. Okay. You need to use Fatou's lemma to pass the the average integral. I'm using the fact that the average integral from t to t plus h of e xr, the limit of this as h goes to 0, this is greater or equal than the energy. Actually, you don't even need Fatou, sorry. You just need the lower semi-continuity of e. That goes. Okay, and you get this. Now, the fact that 3 implies 1, well, is obvious, right? Actually, 3. Let me same as star, but for every t greater or equal than 0 and with. Okay, let me be more precise. 3, I'm asking, so this right derivative taken as lim sup is a pointwise. Okay? It's not the derivative that exists almost everywhere just because the curve is absolutely continuous. For every function, I can compute is like that. And what I'm telling you is that the right derivative at any t greater or equal than 0 is, satisfies that inequality, right? And why this is true? Well, because the integrated version is true for every t and s. So you just write s equal t plus h divided by h and let h go to 0. Okay. So 3 is, sorry, I was not precise. So C holds in this sense. 3 holds in this sense. Now, if 3 implies 1 is trivial because xt is absolutely continuous locally. So this right different quotient for almost every t is equal to the derivative. So that's okay. And what about the fact that sorry, dense, of course, I should have been more precise, dense in energy. So let's speak about 4. What does it mean that I'm requiring the inequality for not for every y, but for every y dense in energy? It means that a set is dense in energy. Remember, this dense in energy. D inside X is dense in energy. If, for every y in X, there exists a sequence yn inside D such that yn converges to y, so that's density. Density in energy means that not only this is true, but the energy of yn is converging to the energy of y. Okay. Sometimes, so in general, the lower semi-continuity of the energy only gives you an inequality here. I'm asking this to be true with inequality. Okay. Well, but now with this definition, it's clear that if I know this for every y when I set dense in energy, okay, pass to the integrate formulation, pass to the 2 for that y, right? And then you see that 2, both sides of 2 are continuous in y as far as also the energy is continuous. Or if you want, write 2 for yn, fix y, pick yn as in here, write 2 for that yn, and pass n to the limit, send n to the limit. Distances converge because I'm not taking any more derivative of distances. So as far as the base point converges, I get convergence of this, and the energy is converged because of density energy. Okay. Okay, let's take a few minutes break, and then we see actual serious properties of the AVIs. Okay, unique. Okay, if x naught is equal to y naught, then xt is equal to yt for every t. Okay, right? So please.
So the energy not obvious.
It's true. It's true.
It is obvious. Energy is higher at some point.
I think you're right. Yes, you're right. Yes, you're right. Yes, of course you're right. Yes, yes, of course. Yeah. I guess what I had in mind is that in a few lemmas I will prove some a priori estimates. So I will tell you how small it is actually. But of course you're totally right. Thank you. I don't need to that assumption. This is true. So you have this quantitative estimate, right? Now you remember that for convex functions on general Banach spaces, the gradient flows are not necessarily unique. Okay, so if you want, a corollary of this is that not every gradient flows of convex functions on Banach spaces typically don't satisfy the VI, because otherwise we have a problem here. Proof. Now there are various ways of proving this, and in fact, to be honest, this existence of geodesic is not necessary, but it makes the proof I think more transparent, so I will keep it. And anyway, it's always satisfied in my situations. So what is that I do? Well, first of all, we know that the amount that xt and returns this distance is absolutely continuous, locally at least, because xt and yt are absolutely continuous curves. So there's no problem in the regularity of this. So I will basically use Grombo's lemma. Okay, and what I would like to do is say k equals 0, just for simplicity. I would like to write this for the curve xt with the point yt as reference point, then revert the roles of yt and xt and add things up. Then the energies of yt and xt will simplify, and I get, in a sense, a differential inequality for the distance squared. The problem is that in general, in a general metric space, so the problem is that I don't know whether these sort of Leibniz rule holds, where this is equal or not to what it is, d s in s equal t of distance squared xs yt over 2 plus the same derivative of distance squared x t ys, right? I would like, some. I mean, if this formula were true, right? I basically the plan that I just stated would work. Okay. Now there are a few ways of handling this. The fact that this formula is not true as I wish, and one way is the following: fix t, and let say s into gamma the s, if you want, be geodesic, geodesic from xt to ys to yt, and write this in the version with this right derivative with as a choice of point you pick the midpoint of the geodesic. So let, if you want, let and pick, and let just for brevity say mt, the midpoint. This is gamma t 1/2. Okay. Then what we know, let me write for brevity this d plus dt of distance squared xt, well, let me write s in s equal t xs mt divided by 2 plus the energy of xt plus k over 2 the distance squared xt mt is less or equal than the energy of mt. Where am I going? Wait a second. Let me think 1 second. I was forgetting assumption. So assume also, actually, I mean, this is not an assumption. So assume also that E is k-geodesically convex. It's not an, in fact, it's not an assumption. In a second, we'll see this will be true. Okay, and that pick gamma is geodesic for which geodesic convexity holds. There is geodesic convex. Is get what I mean? Geodesic. Sorry, I was trying to be minimal in the assumptions, and of course, I removed a few too many. But okay, so okay. Well, so given that I'm assuming that this curve is where the geodesic convexity holds, this energy in the midpoint is less or equal than 1/2 the energy of xt plus the energy at yt, and then I have a correction term which is what it is minus k over 2, k over 8, I guess, distance squared xt yt, right? So, and now I write the same for ys. For the curve, this is, here I used the fact that xt was an EVI gradient. I do the same for yt, and then I get the d plus ds in s equal t of the distance squared between ys and the same point mt. This is the midpoint between xt and yt, plus the energy at yt plus k over 2 distance squared yt mt, which, by the way, okay, we commented this is less or equal than the 1/2, the same thing that is over there. I'm a little bit concerned that there are too many cancellations, I guess. Okay, anyway. So now the observation is this. The observation is this. Let me okay. The observation is this, is that MT is a minimizer for distance squared xt dot plus distance squared yt dot. Okay. If you have 2 points on a metric space, you look at the function distance squared from one point from plus distance squared to the other point. For trivial reasons, any midpoint minimizes this quantity for triangular inequality, basically. Okay. So because given that this is true, if I compute, so what I'm saying, if you want, is that is that the distance squared xt mt plus distance squared yt mt. Well, this I know how much it is, right? Because this is the midpoint. So the distance is 1/2 of the distance. A distance squared is 1/4. So this is 1/2 distance squared xt yt. Wait a second. But for any other, in general, distance squared between xs and mt plus distance squared ys and mt, this typically is greater or equal than 1/2 distance squared xs ys. If you want, by triangular inequality, this is less or equal than distance between xs and mt plus mt y. You expand the squares, use Young inequality, and you get this inequality. Okay. All right, but then you see, okay, now it's just algebra, right? So d derivative, the right derivative as s equal t of distance squared xs ys over 2. Because of this is less or equal than the sum of the two derivatives of distance squared xs mt, divided by 2 plus the symmetric term. Okay. Now you plug the two inequality. You pay more attention than what they did to handle the terms in k. That here there is something wrong. But say if k equals 0, you get basically this derivative is less or equal than 0, which is the end of the proof. Okay. In general, you get the derivative. In general, you should get that the derivative is less or equal than minus 2k distance squared, or minus 4k. I don't know, something. Okay, but I mean the conclusion works. Okay. Okay. I mean, there's nothing beside checking the correct coefficient in front. Okay. So we have contractivity. Yeah, huge property. Another property is the following. And okay, yes. And this perhaps will, this is my excuse for forgetting an assumption over there. And this is another proposition. This is a result by Daneri-Savarin. Around, I think, 2008, if I correctly remember. And the theorem is this. So say that for every suppose that for every x in X there exists an AVI k gradient flow trajectory for E, and assume also that and assume that for every xy in the domain of the energy there exists a geodesic connecting them. Then for every gamma from 0, 1 to x geodesic with finite energy at the marginals, so the energy at gamma naught and the energy at gamma 1 is finite, the curve T, we have the convexity inequality, holds. K convexity too. So this is a metric. So you remember before, when discussing the heuristic behind the EVI, I've mentioned that the EVI encodes, at least in the smooth setting, the EVI encodes both the convexity of the energy and some Hilbertianity of the underlying space. This gives a rigorous justification of what it means that encodes the convexity of the energy. Right? As soon as there are geodesics, okay, connecting points with finite energy, you do have that along any such geodesic, you have decay convexity. Okay. So in particular, if you have EVI K gradient flows, you have more convexity than what you actually typically get from decay convexity. You see? You also get in particular, let me just mention this for the case K equals 0. In particular, the map that takes T and returns the energy along gamma T is actually convex. It's really convex. This is more than what we typically ask for geodesic convexity. Remember, for geodesic convexity, we only typically say that the energy at gamma T is less or equal than 1 minus T, the energy at gamma naught, plus T times the energy at gamma 1. Right? For every T in 0, 1. Right? And I remark that this is less than the convexity, the actual convexity. This is just saying that, you know, and this is 0, this is 1, this is the, and I'm drawing the graph of a, you know, an energy satisfying this assumption, right? So, you know, this inequality is just telling that the graph of the energy is below this line, okay? And you know, for technical reasons related to this, basically typically to the stability of this property, one just requires this. And you can say, well, but it's not convex along, you know, these points. Well, and the answer to this is, well, between this point there will be maybe another curve that is a geodesic along which maybe the curve actually, you know, still does like this, etc., etc., etc. So actually saying that this is convex, you know, is more, okay? And why do I get convexity? Well, because, you know, look at the subinterval. The subinterval is a geodesic connecting points with finite energy, but then, you know, I should have the convexity inequality even along that geodesic. Okay. And the proof, luckily, is trivial. The statement is not, it's deep, but the proof is trivial. Let me do the case K equals 0. What do I do? Well, I pick, you know, fix x y, or say, well, x y, yeah. Actually, fix a geodesic. I fix x and y, and let, you know, gamma be a geodesic, x y with finite energy, gamma be a geodesic, connecting them. And now we write the, so y is a geodesic, so there is, so let me check the convexity inequality at t at time 1/2, okay? For different times is the same. Okay? But let me write this for time 1. You know, so there exists a curve, let's call it, I don't know, ZS, an EVI gradient flow, 0 gradient flow trajectory, starting from gamma 1/2. All right. Well, let me take, you know, definition 2. What do I know? So I use you know, the equivalent property 2 for the curve for this gradient flow trajectory, picking as a reference point y. Once I pick x, and the other time I pick y. Look at what happens. So I get that, you know, I know that the distance squared between ZS and x minus the distance squared between, you know, gamma 1/2 and x divided by 2 plus the average 0s of the energy at ZR. The R, this is less or equal than the energy at x s times. So, yes. Right? Actually, let me do it like this. Okay. And of course, now I do the same with y. Gamma 1/2 y over 2s plus actually the same quantity. This is less or equal than the energy of y. right? Well, but now I add up these two inequalities, and I let S go to 0, and I use, and as before, I use the same this thing. Actually, I use, if you want, I use the what is that I use? I use the I don't even need actually, because this quantity. So the sum of these two is positive. And the sum of these two is positive because the point gamma 1 is a minimizer for distance squared from x plus distance squared from y. Right? Make sense? Right. Here I have distance squared from an arbitrary point, zs, to x, plus distance squared zx to y, minus distance squared gamma 1 of x. This is always positive because these guys are okay. So when you add these things up, what you get, you get twice the average interval from 0 to s of the energy as zr. The r is less or equal than the energy at x plus the energy at y. You let s go to 0, you use the lower semi-continuity of the energy, you know. This is true. And that's the convexity inequality. Okay, at our arbitrary geodesy. So that gives the convexity. Okay, so whenever, so if you have many EVI gradient flows starting from any point, then you actually get convexity. Okay, now I gave you two different definitions of gradient flows in metric spaces. I should really compare them. So let xt be an EVIK gradient flow trajectory for the function E. Then for any epsilon positive, the curve that takes t and returns xt plus epsilon is Lipschitz, and an EDE gradient flow. So gradient flow in the energy dissipation sense. And in particular, this last result is due by Savare. Second, the curve that takes t and returns xt or e to the what? E to the kt as a slope of the energy. These are non-increasing. And 3, we do have the following a priori estimates that I never remember. So yes, we have e to the kt and again, first I will comment this and then I go to the proof. This is true for every y and t. And here I should tell you with this ik of t is nothing but is the primitive. Is the I mean, it's a concise way of writing this e to this kr. Okay. You should think that so in the case k equals 0. So k equals 0, I0 of t is just t. Okay, and it just grows like t. So think of this as this inequality as it st in this inequality, the first approximation. Okay, so let me comment this. So first of all, One tells you, that there is a compatibility. Whenever you have an EVI gradient flow, then you have also a gradient flow in the sense of energy dissipation. Okay. 2 is a regularization property, and 3 are these a priori estimates. And these a priori estimates, I want to stress that these are as powerful. In fact, they are equivalent to the typical a priori estimates that you get for gradient flows of k-convex functions on Hilbert spaces. So basically, even though now we are in the metric setting, if we encode the gradient flow interpretation through the EVI, then you really get, in some sense, the same properties that you get on Hilbert spaces. And let me comment on this. So these estimates are given in terms only of the distance of the initial point to an arbitrary, reference point that we chose. Okay. In particular, on the right-hand side, there is a distance. There is not an energy. For any estimates, for the gradient flow trajectories in the sense of energy dissipation at the, the left-hand side or right-hand side, where it is, there was just the energy at the initial point, right? And because of that, we could only speak really of gradient flows in that sense for initial points that had finite energy. Otherwise, the condition basically trivializes. Okay. While here we are getting rid of the energy and we just have the distance. Okay, and we will see that because of this, this is a crucial technical fact that allows us to speak about EVI gradient flows starting from points with infinite energy. Okay, first remark. Then another remark. I mean, and this is typical in calculus of variation. You have a function on a space, and as soon as you have that, you have a 3 tiers sort of level of regularity. The lowest level of regularity is just the points belong to the space. And improvement regularity is the point belongs to the space and it has finite energy. And the third level of regularity is it has finite energy and also finite slope. Okay. And here we are now distance, and so belonging to the space in some sense, having finite energy and finite slope. And look at what happens when t goes to 0. So this goes to 1, is a constant. This, goes to 0 as t. So I'm saying that t times the energy remains controlled, and t squared times the square slope remains controlled. Okay. No, for instance, if you think, I don't know if you have, this is really, very common. If you think of heat flow, say in L2, then you have L2 functions, is where the function is defined. Sobolev function W12, where the exchange is finite, and functions with Laplacian in L2, that is where the slope is finite. Okay, there are these 3 levels. Or if you have, you work with sets of finite perimeters, you have arbitrary sets with finite perimeter, and typically you have these local minima or quasi-minima of the perimeter that are those basically where the slope is finite in some sense. That is more, but you only it's kind of that goes in that direction. Okay, let's do this. So this local Lipschitz regularity is quite easy, because for every epsilon, this curve is still an EVI gradient flow trajectory. If you rescale in time, you go forward in time, there is nothing that prohibits this to the gradient flow, right? Now I got into trouble. Let me say, okay, so what I want to conclude is that then the distance between xt plus h, actually s plus h and s, I want to say that this is less or equal than the distance, or e to the kt, the distance between s minus t, right? Is xt plus epsilon and xt for every t less than s. Okay. What I want to say is this, right? Because I have 2 EVI gradient flow trajectories, right? Let me start from the point xt, or from the point xt plus epsilon, and let me flow for a time equal to s minus t, s is bigger than t. Then xt goes to xs, xt plus epsilon goes to xs plus epsilon, and then this contractility. Right. So pick a point. T at time t where the speed is finite. No? Xt is a locally absolutely continuous. So for almost every t, there's a metric speed. Okay, fix such t, no? and then fix t. So for t, such that the limb as epsilon goes to 0 of the distance xt plus epsilon xt divided by epsilon is finite. If you want, fix this. Then what this inequality is telling is that for every s bigger than t, this limb sup is also, if you want the metric speed, let me put this way, the metric speed is less or equal than this limb sup for almost every s bigger than t. Make sense? Right? But if the metric speed is bounded, the curve is Lipschitz. Right? It's just contracting. No? Sometimes it just goes lower and slower. Of course, I slightly cheated because I only know this if I have this assumption about the existence of geodesics, at least in the previous lemma. So if you want, add that assumption if you wish, or find a way that is possible to prove this contractility estimate even without the existence of geodesics. I mean, any of the two works, but let me, in some sense, be a little bit fuzzy here. So add the assumption if you wish. I mean, the existence of geodesics in the domain of the energy, it will always be the case for us. Now let's prove that these EVI gradient flows, that they do satisfy the energy dissipation, which seems a bit crazy. We have this. This EVI is a way of controlling the derivative of the distance squared in terms of the energy, and this actually implies that this energy dissipation formula holds. So let me prove this in the case k equals 0. There is no additional complication except in writing formulas, but no concept of complication in proving that these are the dissipation formula for the energy works. Now, first of all, notice that if I rearrange the terms in the EVI, in the formulation of dVi, what I get is that the energy of xt minus the energy of y for every y divided by the distance between xt and y. This is less or equal, if k is equal to 0, this is less or equal than 1 over twice the distance between xt and y times dt of distance squared xty for every y and almost every t. You agree? This really comes just by rearranging terms in dVi. Okay, 1/2 distance squared, derivative of distance squared is less or equal than energy of y minus energy of x. So I'm just swapping the derivatives. Okay, maybe there's a minus. Okay, well, but this by the chain rule, this is equal for almost every t minus the derivative of xty, which of course is bounded from above by xt naught for almost every t. Make sense? Right? So in particular, so this quantity for every y, this quantity is bounded, for almost every t, this is bounded from above by that quantity. So I can, which is positive. So let me take the positive part in here. Positive part. This is positive, and what I get now, I send y to xt. I cheat a bit about fixing t and y and swapping. So a priori, this for almost every t is almost every t that a priori should depend on y, but in fact, for every t for which this is metric speed is well defined, this inequality holds with the limb sup. Okay, so I know that for almost every t, this inequality holds for every y. And now I let y go to xt, and what I conclude is that the slope of E at xt is bounded from above by the speed for almost every t. And that's, the first piece of information. A second piece of information is, of course, if I now pick here instead the y equal to xs, okay, what you get is that the energy of xt minus the energy of xs divided by the distance between the two is bounded by the speed. Okay, but now if you swap this. Basically, you're telling it this is bounded by the max of these two, okay? And this is bounded by, if T and S are bigger than some epsilon, this is by the what we already proved about local ellipses of graph, this is uniformly bounded. So I'm proving that the map that takes T and returns E of xt is local ellipses. Make sense? Right? Because as soon as I pick T and S bigger than epsilon, this is actually ellipses. Okay. Okay, so it is local ellipses, so it is differentiable almost everywhere. So I can compute minus dt of the energy of xt. Okay. This derivative is the limit as h goes to 0 of what do I do? The energy of xt minus the energy xt plus h, because there is a minus, so the h in some sense goes with the minus sign, and then I divide by the distance between these two. I multiply by the distance between these two. Divide by h. Okay. Well, then, of course, well, let me, this is less or equal. Let me take here the positive part. And when h goes to 0, this, and if t is a point where the metric speed exists, this is, the bounded from above by the slope times the metric speed, right? So by Young inequality, this is bounded by the speed squared, 1/2 plus 1/2 the slope squared, right? For almost everything. Okay. So and this is the second inequality. If you want to look at it. So I have 1, 2. Okay. Now it comes the third and last inequality. So the energy dissipation formula is something that relates the dissipation of the energy, the metric speed, and the slope. And basically it tells that the three agree up to squares and factors 1/2 and so on and so forth. So I'm writing down 3 inequalities that combined give this. And the last inequality is this. Pick, what do you pick? Pick y equal to xt in this. And you get the distance squared between xs and xt divided by 2 plus, actually it's less or equal, then the integral from t to s of the energy of xs minus the energy of xr in the r. Case 0, so that term with the case drops. Okay. This is equal, let me rewrite this. This is equal to the integral from 0 to 1 of the energy of actually of s minus t is the factor, and then I have the energy of what I have x, I guess, t plus h time s minus t minus the energy of xt, I guess, dr. Is correct? No, no, it is not. Wait a second. No. Sorry. I mean, sorry. So here I should have, sorry, I pick, sorry, y equal x, sorry, y equal xt in 2. Y equal xt, sorry. Y equal xt. So this term drops out. I have distance squared xs xt. This term gets out, so I get the energy of xt minus the integral, the energy of xt minus the integral of this. Sorry. Now I rescale this integral. I change the variable, and this is the integral of energy xt minus the energy of x at t plus s minus t times h, if you want, the h. Right? Now, if you divide by s minus t squared, and you let s go to t, what you get is that the speed squared over 2 is less or equal, you know, that the lim when h goes to 0, when h is a terrible name here. Let me put r here. R. Limit as h goes to 0 of the interval between 0 and 1 of energy of xt minus the energy of xt plus h times r divided by h in the r, right? But now by you know, if you pick a point where this guy, where the energy as a function of time, energy of xt is differentiable, you see that this is really equal to minus the derivative of the energy of xt, you know, for almost everything, right? And this is the third inequality. Okay, there is a factor 2 somewhere. There should be a factor 1/2. Sorry, 1/2. The 1/2 counts because basically this is basically you know, I should think this is kind of the derivative of ext times r, right? So when you integrate r from 0 to 1, you get 1/2. Okay, so this is the third inequality. You know, the speed is bounded from above by the dissipation. The dissipation is bounded from above by a combination of speed and slope, but the slope is bounded by the speed. Put these three together, and the claim is proved. All right. Now I had to prove that the functional is decreasing or non-increasing in time, and now this is obvious by the energy dissipation formula. And that the slope up to this exponential factor is also decreasing in time, but at least for almost every t, I know that the slope is equal to the speed, and the speed decreases in time, right? Because of by this. So up to some almost everywhere that I should handle, I sort of almost prove that the slope is decreasing. Okay. Let me conclude the proof of the a priori estimates. Again, I'll do this in the case k equals 0, but the point is this. Let me compute t squared over 2, the slope squared in xt. I claim now, given that, forget about this. In t, this is decreasing. This is less or equal than the integral from 0 to t of s, of s slope squared in excess in s. Right. In fact, I proved that for almost every s smaller than t, this is bigger than this quantity, right? So then you integrate s and you get this. Okay. But I also know that this is the derivative of the energy, right? By what we just proved. So this is equal to the integral from 0 to t of s times. Okay, I should write this of minus the energy of excess. But given that I'm a little bit lazy and I want to, I fear of making confusion with the integration by parts formula, let me write like this. This term does not depend on s. So I can add this. And I have the advantage that when s is equal to 0, I want to integrate by parts. And then when s is equal to 0, this term is 0 for the boundary term. And when s is equal to t, this term is 0. So when I integrate by parts, I don't get boundary terms. And this is just the integral from 0 to t of the energy of xt minus the energy of xs ds. Is this correct? No, it should be minus xs. Why is that? I should have the other sign. Why is that the case? Yes, because I integrate by parts. Sorry, because I'm integrating. Sorry, of course. Okay. Okay. Now what do I use? Okay. Now I use the EVI. The EVI is telling me. So forget about the integral. I know. Let me write it here. What I'm using so that you see it more clearly. I'm using the fact that ds of distance squared xsy over 2 plus the energy at xs, this is less or equal than the energy at y. For any y and almost every s, this is true, right? So the energy at xs is bounded from above by, I still have this term, this piece, this I leave untouched. This is bounded from above by the energy at y plus ds of this distance called xsy over 2 ds. Sorry? Minus. Thanks. Minus. Thanks. Okay. Okay, now this is less or equal than what? Okay, this guy and this guy do not depend on s. So this is just t times the energy at y minus the energy at xt. And here I'm integrating this distance squared. So this is, I have the 0, because of this minus, the 0 term comes with a plus. So plus distance squared x0 y over 2 minus some distance squared which is positive, and therefore I forget. So I have a less or equal. And you see, this inequality with k equals 0 is precisely this. You know, I have wait a second. No, wait a second. No, I keep the term. Sorry, I keep the term. I don't throw it away. Xt minus y divided by 2. Sorry. This is equal. I don't throw away this last term. So I have the distance squared xt y over 2. If I bring to the left, comes with the plus. Where this I bring to the left, it comes, with the correct sign, in that sense, as written here. Plus t squared over 2 slope squared. This is bounded from above by this guy over here. Okay. Okay, let me conclude. Let me just conclude with the following observation. And this will be, in some sense, the starting point. Okay, or perhaps a starting point of next Friday's lecture. So an observation is the following corollary. So let E from our metric space to 0 plus infinity be such that for every x belonging to some d dense in x, not in energy, there exists a gradient flow, an EVI k gradient flow trajectory starting from x. So assume that you have existence of EVI k gradient flow trajectory, not for any initial point in the space, but just on a dense set. Well, then existence is in place for every initial point. All right. And okay, so how would I like to prove this result? Well, what I would like to say is, okay, look, pick x in x and xn in this dense set converging in x. Right. For each of these, I have x and t. Right, the corresponding gradient flow trajectory. by the contractility estimates, say that the space has geodesics if you want, sufficient geodesics, then by the contractility estimates, I know that the distance between x and t and xmt is bounded by what is e to the minus kt, the distance between xn and xm. Right? This is true for every t. Right? So whenever the initial points are converging, the corresponding EVIK gradient flow trajectories are converging locally uniformly somewhere. I mean, locally, by space is complete, so they converge locally uniform. Okay, so it exists, a locally uniform limit. Call it xt, and clearly this is a curve that starts from x. Okay. Also, clearly satisfies too. Right? Because if you write this for every n, right, and then you pass through the limit in n, you see that there is, the distances converge. For the energy, I typically only have lower semi-continuity, but the energies, are on the left-hand side of the equation, on the lesser equal. So, how to allow me to pass the limit on the energy? Okay. So, for trivial reasons, any pointwise limit of EVI gradient flows satisfies this inequality. Okay. So then, why I did not, stated this corollary 1 second after having given the definition of EVI? Because a priori it is not trivial, and I should work a little bit to prove that the limit curve xt is absolutely continuous. This is just a uniform limit, so in principle, just a continuous curve. Okay. How do I get absolute continuity? Well, from these a priori estimates. Which I erased? Okay. No, from these a priori estimates. Okay. Because thanks to these a priori estimates, I know in particular that the energy, fix any y with on the space. Forget about this positive term. Forget about this positive term if you wish, or keep whatever you want, and fix y with finite energy so that this is not minus infinity. And what you get is basically the sup in n of the energy of x and t is finite, for every t positive. Okay. But now from the energy dissipation, formula, you know that the energy at x and t is equal to the energy at x and s plus the integral from t to s of the speed squared of this curve. Okay. So this is non-negative. Let me throw it out. This is bounded by some constant, and you get, the uniform bound in n. You fix t and s positive, right? And you get a uniform bound in n of the energy of these curves in that interval. Now, uniform bound, this on the two energy, this passes to the limit, and thus that the limit curve is also absolutely continuous. Okay, at least locally. Okay, so some work of this form has to be, done in order to be sure that you have, an absolutely continuous curve. And all right, so there is one last thing that I wanted to mention today. Perhaps let me just draw a picture, and then Friday we start from this picture. Because I've mentioned that, so just to wrap things up, we have two notions of gradient flows of k-convex function. One which is based on the energy dissipation equality, and the other one which is based on the on this evolution variational inequality. And whatever definition you have, typically you are concerned with existence, uniqueness, and stability. Now, I've mentioned that for this concept of gradient flow of convex function, we typically have existence where we don't have existence for EVI. Okay, because if we had existence, for EVI gradient flows, these EVI gradient flows would also be EDE gradient flows, so they should be contractible. and unique, but we have examples of convex functions on Banach space where we don't have uniqueness. So in particular, typically we don't have existence. Conversely, for the ED gradient flow, we typically don't have uniqueness, as just mentioned, but for the EVIs we get, actually we have more, we have contractivity. Okay. What about stability? We have already mentioned the stability of this and the uniform, K convexity property. And we will see that in fact, even there is also stability at the level of the EVI. This we will mention at the beginning of Friday's lecture. So there are two different ways of working with gradient flows. In some sense, the basic theory works with this. But if you are in a situation where you also have existence for the EVI K gradient flow, then that point of view typically works better. Okay, when it is available. Okay. Okay, so end of math, a couple of communications. So next week there will be no lecture because there's the conference on aspects of Ricci bounds, and perhaps let me make explicit something that I mentioned to a few of you informally. So for those of you who, you and whoever else is going to take the exam, or we need to take the exam for this course, the exam will consist basically on an oral presentation. So a few weeks we arrange things. A few weeks before the exam, the student comes to me and says, okay, I want to do the exam, and then I give him to read something concerning the topic of the course. Could be, I don't know, sober functions, could be EVI gradient flows, could be, some topic. I give him something to read, and then a presentation of say half an hour or something like that on that topic. Okay, and that's it. See you on Friday.